So continuing with our phase plane analysis of this differential equation, x dot equals x minus y minus x cubed, and y dot equals x. What we just saw was that if we chose this initial condition, the solution sort of wraps around and converges onto what could possibly be a periodic closed orbit. And it is indeed a periodic closed orbit. It's a stable periodic orbit, also called a limit cycle solution. And this trajectory, as you go in forward time, crosses the nullclines in the correct orientations and eventually wraps around onto this periodic closed orbit. Now, let's click in several other locations and sort of get an overall sense of the flow. Remember, when I'm doing this, the integrator is going in both forward and reverse time. So I think it's now becoming pretty clear what's happening. And one thing that I want you to note that is that the solutions are moving, a lot of the time, they're moving in almost horizontally. And that is an indicator that x is actually a faster variable than y. If x is changing more quickly than y, the solution would have a low slope in this plane, correct? And that's something to take note of. And what will happen with these solutions is that x will quickly change, and you'll get until you get to relatively near to the x nullcline, and then you will move along the x nullcline in the direction indicated by the arrows. And you can see that happening up here on this branch of the x nullcline, and this branch of the x nullcline as well. Now, another thing that we can do is pick an initial condition that's close to the steady state at the origin. And to do this, I'm actually going to change the options. Now, you can't see this right now, but I'm changing the options to make the solution direction only forward. And now I'm going to click to a spot, click on an initial condition that's relatively close to the steady state at the origin. And what you can see is that the solution spirals out and eventually sort of asymptotically approaches the limit cycle solution that we had already seen. I'll do that in several different locations. So it looks like, just intuitively, that this steady state at the origin is a unstable spiral, because the flow is moving away from the steady state, and you can visually see the spiraling. So now what I want to show you to do is that you can confirm this impression that the steady state at the origin is an unstable spiral, that you can confirm this analytically. So let me bring up our phase plane sketch, and I'll clean up a little bit here. We have a steady state at the origin, we know that, and let me remove the nullcline information here. And what I'll do now is try to analytically show that the steady state here at the origin is an unstable steady state. Now, the way that this stability analysis is performed in two-dimensional systems is to linearize the ordinary differential equations near the steady state. And what that means in practice is that we're going to calculate this matrix that's called the Jacobian, which could potentially be the function of x and y. And it will be a 2x2 matrix where in the upper left-hand corner we'll have the partial derivative of the first equation, which we often write as f, with respect to x. And then the partial derivative of the first equation with respect to y. And down here we'd have the partial derivative of the second equation with respect to x, and the partial derivative of the second equation with respect to y. Now I'm in that partial derivative notation, I'm saying that the right-hand side of the first differential equation is the function f. And the right-hand side of the second differential equation is the function g. All right, now taking these partial derivatives is not difficult. The first equation, the derivative with respect to x, is just taking the derivative of this polynomial holding y fixed. So if y were a constant, the derivative of this polynomial would be 1 minus 3 times x squared. And the derivative of this polynomial with respect to y is minus 1. The derivative of g of x and y with respect to x is 1, and the derivative with respect to y is 0. So let me clean up that ugly matrix right there a little bit. I'll just put the final answer down. The derivative with respect to x of the first equation was 1 minus 3x squared. The derivative with respect to y was minus 1. The derivative of the second equation with respect to x was 1. And the derivative of the second equation with respect to y was 0. And now, in order to evaluate the stability, we simply take this Jacobian and actually evaluate it at the steady state. Now, the steady state here is 0, 0. So this Jacobian evaluated at the point 0, 0 is, well, now it'll be a 2 by 2 constant matrix. If x is 0, then the first entry here is a 1. And then there's no other dependence on either x or y. So this is the constant coefficient Jacobian matrix that's relevant at the steady state. Now, in order to determine whether it's stable or not, we simply need to calculate the trace and the determinant of this matrix. And the stability condition is that the trace must be negative and the determinant must be positive. If those two conditions hold simultaneously, you know that the steady state is stable, and they are required for the steady state to be stable as well. So let's just calculate the trace of this Jacobian matrix. Now the trace is the sum of the two diagonal elements, so that's 1 plus 0. The trace is 1. And the determinant of the Jacobian matrix is the product of the diagonal entries, 1 times 0, and then we subtract the product of the alternate diagonal. So this would be minus 1 times 1. So the first term is 0. The second term is the opposite of negative 1 or positive 1. Now, because the trace is positive, straight away we know that the stability condition is not satisfied. recall the stability condition is that the trace needs to be negative and the determinant needs to be positive. Both things need to be true. So the positive trace tells us that it's an unstable steady state. And if we wish to further classify this unstable steady state, we could have a look at the trace determinant plane. So before I show that, let me remind you that some authors will use the Greek letter beta for the trace and gamma for the determinant. And so in our case, both the trace and the determinant, both beta and gamma, are equal to 1. And we can just look up on the trace determinant plane on what type of steady state this is. So there's the trace determinant plane. This is one of your slides from class. And when the determinant is positive, we know it's not a saddle. And when the trace is positive, then we know that it's either an unstable spiral or an unstable node. And the difference depends on whether you're above this parabola or below it. To determine whether you're above or below the parabola, this is a comparison between beta and gamma, a comparison between the trace of the Jacobian and the determinant of the Jacobian. And here you can see that for an unstable spiral, we have to have a positive trace, and the square of the trace must be less than 4 times the determinant. And that's the case for us because beta is 1 and gamma is 1. And 1 squared is less than 4. Now at that point we know we have an unstable spiral. And that's consistent with what we saw in our numerical calculations, where solutions near the steady state spiraled outward and then eventually limited on a periodic solution, a stable periodic orbit that looks somewhat like that. Also, the solutions that, one of our first solutions that we calculated numerically started over here and sort of slooped around like this, got on or close to the x nullcline, crossed it, and then sort of hugged the x nullcline, and then landed on the stable periodic orbit. So you can sort of see that both of those solutions in the phase plane are quite consistent with what we've calculated sort of analytically here. And just one more thing, I find this final determination of whether this was a spiral or a node, I think it's most intuitive to think of the trace determinant plane with this parabola. Since this is the determinant on the horizontal axis and this is the trace on the vertical axis. Remember, this is gamma, this is beta. The condition for this parabola can be written several ways, but I think it's best to write it as gamma equals beta squared over 4. Because then, if the determinant is larger than this number, you know that you're in this region. So I'd also write that this way. The determinant of the Jacobian would be compared with the trace squared divided by 4. So this I said compared with. This equality is determining where the location of this parabola. And since above the parabola you have the spiral solutions, you would want to compare the determinant with the size of the square of the trace divided by 4 to determine whether a solution was a spiral or not. So I hope this helps. See you in a few days.